Hello, chemists. Let's continue talking about hybrid orbital theory. All right. In the last video, we talked about being able to overlap atomic orbitals and to be able to make these things called hybrid orbitals. Well, what we're going to do now is we're going to use those hybrid orbitals to predict these single bonds, double bonds, triple bonds. So here, if I have, we're just going to do carbon again. So we have 2s and we have 2p. Now, if I don't put the valence electrons in, it looks like I have 3 bonding places, but they are not the same energy. Okay, and that's an important point because we know if we have a carbon, it can form 4 identical bonds, and I'll just put hydrogens here. They're all identical with the same energy. And so we needed a theory that could help explain that. And so we can't use the atomic orbital because that's just dealing with the atom. And so the hybrid orbital theory says if there's the potential of a bonding place, it's going to hybridize. So it's no longer going to be just an S or just a P. They're going to turn into, and this is where we hybridized them. And if we use 2 of them, we called it SP and then the leftover Ps. So these are the hybrids. Those are the leftovers. Or we could have 3 sp2s plus 1 leftover p, or we could have 4. And there's nothing, okay? Unless you're out into the D's, I used up all of the S's and the P's. So this would be an sp3. Now the beauty of it is, this is 4 bonding places. This is 3 bonding places, and this is 2 bonding places. So when we were doing Lewis structures, the carbon, when we drew 1, 2, 3, 4, and I said, what are the loners? Those are bonding places. It was using sp3. When we made a double bond to carbon, it only had 3 locations, so that was sp2. And when we either did 2 double bonds or a triple bond, that was using sp. And if you'll notice, when I went to sp2 and sp, this thing showed up called a multiple bond. So that's a double, 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 or triple. And hybrid orbital theory is going to help us visualize that. So the first thing, what can live in a hybrid? First of all, you don't form a hybrid unless you need it. Okay, so you're never going to leave a hybrid orbital empty. And what can live in a hybrid is either a lone pair or something called a sigma bond. And a sigma bond is the overlap. It gives the nice little Greek symbol sigma there. So sigma, when I drew this, that overlap right there, that is a sigma bond. And it has free rotation. So 360-degree rotation. So basically, if you held on to one, the other could go whee, and could just rotate around it. Okay, that is called a sigma bond. A lone pair, of course, we've already seen those. So a lone pair would just be a lone pair. And that's what can live inside of a hybrid. Well, what can live out here in these leftover atomics? It can either be empty, or it can participate in something called a pi bond. And a pi bond is basically a multiple bond. So a pi bond is the second portion. So if you want to form a double bond, the first thing you have to create is that true overlap, which is a sigma bond. And then you get that interact that I was talking about, those 2 p orbitals. So the first thing, remember, always formed is a sigma, and then you can overlap. Erase here. And we're going to have a carbon come along, and it is going to have an SP, and an SP. And then what is still available? Remember, these are the, we'll just call that one the PY, the PZ. Well, if another carbon comes along, it can overlap. It can overlap two hybrids, and that now forms a sigma bond. But guess what it already has? Or it also has. It has a PY and a PZ. And that is what I call the interact. So the PZ lobes interact together, and the PY lobes interact together, and those are the pi bonds. And so one pi bond takes up both lobes of a p orbital. So a PY and a PY, that's a pi, or the PZ, PZ is a pi. So I call that an interact. And then this one would be a true overlap. So a double bond is made of one sigma and one pi. A triple is made of one sigma and two pi's. And then, of course, we'll just put single here. A single is just sigmas. A single is just sigmas. And that's the idea behind multiple bonds. The first thing that always has to form is the sigma, a true overlap. But then the interactions make it both stronger and it also makes it shorter. So these atomic orbital interactions, they pull it in tighter. So they pull the two atoms tighter, which makes it shorter. And they're overlapping, and there's three parts to a triple bond. So they're overall stronger. Right? And then how many electrons is it? So we'll draw a single bond, we'll draw a double bond, we'll draw a triple bond. All right, so we've got our sigma, our sigma, our sigma. And then we've got a pi, we've got a pi, we've got a pi. Now, a sigma is one thing, a double is one thing, and a triple is one thing. That's a bond, but it's made of three parts, two parts, and one part. And so that's why you get the different lengths and strengths. So for lengths, a single is much longer than a double, which is longer than a triple because they're getting pulled in tighter. But as far as strength, now I'm talking about cleaving all the way through. Okay, so cleave all the way through. A triple is stronger than a double, which is stronger than a single. But if you're only talking about the individual types, a sigma bond is always stronger than a pi bond. Okay, now remember, a triple is one sigma and two pi's. But if you're talking about just the individual pieces, a sigma is always stronger than just a pi. And wow, that was a whole lot of words. Are there any examples that we can see? And so the best way to do this is to draw a little structure. So we're going to, of course, I'm an organic chemist. So we're going to draw the organic molecule. Mm, mm, mm. So there's an example of a crazy organic molecule. What we're interested in is, whoops, I just lost my whole picture. What we're interested in is determining what the pieces are made of. So let's figure out the lone pairs first. Those are usually pretty easy. So this is a lone pair, that is a lone pair, a lone pair, a lone pair, and a lone pair. Okay, so there's 1, 2, 3, 4, 5 lone pairs. How many pi bonds are there? 1, 2, 3, 4. And it looks like there's a total of 4 pi bonds. All right, now how many sigma bonds? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. So there's 18 sigma bonds. There are 1, 2, 3, 4, 5 lone pairs. And pi bonds, there was 1, 2, 3, 4. Can you visualize what the hybrid would look like for each of those? And so we're going to go along and we're going to put what the hybridization is. Every atom has a hybridization state, except hydrogen and helium, because hydrogen and helium, well, they don't have access to anything but the S's. So I'm going to not touch the hydrogens, but I'm going to go through and I'm going to look at all the other atoms. And so this carbon has 1, 2, 3, 4 around it. And so that is family 4, but family 4 is really a variation of sp3. And so this one, different color, this carbon has 1, 2 things around it. So that carbon's sp. Well, this carbon has 1, 2 things around it. So it's sp. Another color. This one has 1, 1. Can't see that. It has 1, 2, 3. And remember, a double bond is one thing. So that is sp2 hybridized because it has 3 things. This one has 1, 2, 3. So it's sp2 hybridized. Let's see, green. This oxygen has 1, 2, 3. And remember, every atom has a hybridization except hydrogen and helium. So that's an sp2. And we have yellow. This one, whoa, I just made that gigantically big. 1, 2, 3. And so that's sp2 hybridized. 1, 2, 3, 4. So that one's sp3. 1, 2, 3, 4. So that one's sp3. The nitrogen has 1, 2, 3, and 4. So it's sp3. All right, so take home message. The family is also the hybridization. Okay, so the family is also the hybridization. And now I'm going to draw out the hybrid orbital diagram for each one of these. So we're going to label this one carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6, carbon 7, and then this is oxygen. We'll just call it 8. We'll call this oxygen 9, and we'll call that nitrogen 10. All right, so carbon number 1 is sp hybridized. So it is doing this. And how many valence electrons does carbon have? Well, it has 4. So it has the potential for 2 sigma bonds and 2 pi bonds. Carbon number 2 is also sp hybridized. So guess what? It also has the potential for 2 sigma bonds and 2 pi bonds. Now we know they're bound together. So there's the sigma bond. And then here's the first pi bond, and there's the second pi bond. But if you'll notice, I still have two bonding places. So that means it is attached to two other things. Now, one of them is a hydrogen. So I would just draw this because it doesn't hybridize. So that's one hydrogen. All right, that takes care of carbon 1 and carbon 2. How about carbon number 3? How about carbon number 3? Now, it has 4 things around it. So carbon 3 is 1, 2, 3, 4. And it has 4 valence electrons. Keep them unpaired for as long as possible. So it's going to have the possibility of 4 sigma bonds. And it has a hydrogen, and then a carbon and a carbon. Now notice there is no pi bond, okay, because it doesn't have access to the p's. Carbon number 4 right here is sp2 hybridized. Has 1 leftover atomic, and so it has the potential of 3 sigmas and 1 pi. Carbon number 5 is also sp2. And based on this picture, we have 1 sigma bond between them and 1 pi, which leaves 2 sigma bonds for each of them. And carbon, what number is that? Carbon number 6 is also sp2 hybridized. Oops, I didn't draw enough lines. sp2. And 1, 2, 3, 4. So again, it looks like I can have a double bond. Oxygen number 8. 1, 2, 3. Oh, guess what? It's also sp2 hybridized. All right, now it has a different number of valence electrons, though. 1, 2, 3, 4, 5, and 6. So this has the potential for 1 sigma bond and 1 pi, but remember, they have to go together. So this is my pi bond between them, and then that would be my sigma bond between them. All right, oxygen number 9 looks like it's just sp3, and it has 6 valence electrons. So 1, 2, 3, 4. Oh, look, it's telling me that there's 2 lone pairs and 2 sigma bonds. Carbon 7 is 1, 2, 3, 4. So it has 4 good bonding places. And then the nitrogen is 1, 2, 3, 4. And it has 5 valence electrons. So it's telling me that nitrogen will have 1 lone pair and 3 sigmas. All right, that either was like, oh yeah, I get it, or you might need to look at it a couple times, but I walked through that in the handout. But that, in a nutshell, is hybrid orbital theory, and it gives us a little bit of some predictive tools. So as a recap, how in the world can you predict? Because remember, ionic is easy to get off the periodic table because you just have to balance charges. But nonmetals and metalloids, you have to know what their potential is. So if you have S's and P's, your choice is you may do SPs with leftovers, SP2s with a leftover, or SP3s with none left over. Okay, and so that's all you get. Well, what happens if you move into the row 3? Well, you have access to the D's, and this is why expansion can happen. So you have S's, 1, 2, 3 P's, and 1, 2, 3, 4, 5 D's. And remember, you always have to start low before you go high. So you could make 1, 2, 3, 4, 5. That would be called an sp3d because I used the S, all 3 P's, and a D. And then there's 1, 2, 3, 4 D's left over that can be empty or can pi bond. Or you could go 1, 2, 3, 4, 5, 6. And that is sp3d2 with 3 left over. And you lovingly know them as family 1, which is linear at 180 degrees. You know this one as family 2, which is trigonal planar at 120 degrees, but it has the potential of a pi bond. This is family. I don't know why I said family 1 and family 2. Sorry about that. Family 2, it has 2 parts, so that's linear. Family 3 is trigonal planar. Family 4 is tetrahedral. And so if you don't have access to the D's, you are stuck with 109.5. But guess what? Family 5 has 6 spots, and so we call that trigonal 5-pyramidal. And now you have to take into account the different locations. And then family 6, which is octahedral. And then you'd also have to know which location if you want to talk about the angles. So it's just a one step more complicated version, but it's going to give us the power of prediction. What could the atoms possibly do if they came close enough together? And that takes care of hybrid orbital theory. All right, until next time, jolly out.